One of the most fascinating and enduring mysteries in modern physics and cosmology is the question, why does the observable universe consist almost entirely of matter, while antimatter, which should have been produced in equal amounts during the Big Bang, is practically nowhere to be found. This asymmetry between matter and antimatter challenges our understanding of the fundamental laws that govern the cosmos. According to the standard model of particle physics and the Big Bang theory, matter and antimatter were created in equal quantities when the universe was born nearly 13.8 billion years ago. Each particle of matter should have had a corresponding antiparticle, identical in mass but opposite in charge. When matter and antimatter come into contact, they annihilate each other in a burst of energy, leaving behind pure radiation. So, if both were created in equal amounts, then the early universe should have seen mutual annihilation on a massive scale, leaving behind nothing but light, no galaxies, no stars, no planets, and certainly no human beings. Yet, here we are. This paradox raises a profound question: why did matter win? Why was there even a slight excess of matter, perhaps as little as 1 particle per billion, that didn't annihilate and instead went on to form everything we see in the universe today? Scientists refer to this imbalance as the baryon asymmetry of the universe, a BU. If the laws of physics treat matter and antimatter exactly the same as we once believed, then such an asymmetry shouldn't exist. The universe, however, has a different story to tell. The very fact that we are made of matter, and not of energy alone, suggests that somewhere in the earliest moments of the universe, something happened to break the perfect symmetry. Understanding this mystery is more than just a scientific curiosity. It's a window into the deepest workings of the universe and our place within it. Various experiments in particle accelerators, cosmic ray observatories, and astrophysical surveys have been conducted to search for traces of antimatter or any clues that could explain its disappearance. While we've discovered phenomena like CP violation, which hints at differences in the behavior of matter and antimatter under certain conditions, these observations are not yet sufficient to fully account for the dominance of matter. The stakes of this question are enormous, not just scientifically, but philosophically. If we can answer why the universe favored matter over antimatter, we may also answer how existence itself is possible, and why reality turned out the way it did instead of remaining in a state of perfect balance that would have left it forever dark and lifeless. To grasp the mystery of why the universe contains more matter than antimatter, we must first understand what these two entities really are. Matter is everything we interact with in our everyday lives: atoms, molecules, stars, galaxies, and even ourselves. It is composed of elementary particles such as electrons, protons, and neutrons. Antimatter, on the other hand, is composed of antiparticles, counterparts to every known particle of matter. For instance, the antiparticle of the electron is called the positron, which has the same mass as an electron but a positive electric charge. Similarly, the antiproton has the same mass as a proton but carries a negative charge. When a particle meets its antiparticle, they annihilate each other, producing energy usually in the form of gamma-ray photons. The discovery of antimatter wasn't merely theoretical. It was first predicted by physicist Paul Dirac in 1928 through his formulation of a relativistic quantum theory of the electron. In 1932, the positron was discovered experimentally by Carl Anderson while studying cosmic rays, confirming Dirac's predictions. Over time, scientists found antiparticles for almost every known particle. Antimatter is not just a curiosity. It behaves in every measurable way like regular matter, except for the crucial difference in charge and quantum properties. Antimatter can be created in laboratories and has practical applications, such as in medical imaging through positron emission tomography PET scans. However, antimatter is extremely rare in our observable universe. Whenever antimatter comes into contact with matter, which dominates the cosmos, it annihilates instantly. This makes it nearly impossible for large structures of antimatter, like anti-planets or anti-galaxies, to exist in a universe that is already flooded with matter. If entire regions of the universe were composed of antimatter, we would expect to see a constant and observable stream of high-energy photons at the boundaries where matter and antimatter regions meet. Yet, we don't see this, which supports the conclusion that the observable universe is almost entirely matter-dominated. This leads to an inevitable and puzzling conclusion. Something happened early in the universe's evolution that tipped the balance in favor of matter. The fundamental question is not whether antimatter exists. We know it does, but rather why so little of it remains compared to matter. Why wasn't the original 50-50 balance preserved? Answering this question requires diving deeper into the laws of particle physics and the earliest fractions of a second after the Big Bang, where even tiny asymmetries could be amplified into the cosmic structure we observe today. The central mystery in the matter-antimatter question lies in the imbalance that occurred just moments after the Big Bang. This tiny but critical difference in the quantities of matter and antimatter is known as baryon asymmetry. In simple terms, for every billion pairs of matter and antimatter particles that annihilated each other, there was one extra matter particle left behind. That tiny surplus formed all the matter in the universe today. The question is, what process created this surplus? This is where the famous Sakharov conditions, proposed by Russian physicist Andrei Sakharov in 1967, come into play. He outlined 3 essential criteria that must be met for an imbalance between matter and antimatter to develop in the early universe: baryon number violation. There must be interactions that do not conserve the number of baryons Z particles like protons and neutrons. C symmetry and CP symmetry violation. The laws of physics must not be entirely symmetrical when particles are swapped with their antiparticles sub C symmetry, and when spatial coordinates are reversed to P symmetry. CP violation. The combination of charge conjugation and parity is especially important. Departure from thermal equilibrium. The universe must have experienced moments where it was not in a balanced thermal state, allowing asymmetric processes to have lasting effects. CP violation has been observed experimentally, most notably in the decay of K mesons cons and B mesons, through experiments such as Babar in the US and Bell in Japan. These experiments showed that certain particles decay into their matter and antimatter forms at slightly different rates. A critical discovery. More recently, the LHC experiment at CERN has continued investigating these asymmetries in greater detail. While these findings confirm that CP violation exists, the level observed is not nearly enough to account for the massive imbalance we see in the universe. This means that new physics beyond the standard model is likely needed to fully explain the phenomenon. Another important consideration is the potential role of neutrinos, extremely light and elusive particles that are still not fully understood. The process of leptogenesis proposes that a lepton-based asymmetry involving neutrinos might have preceded and led to the baryon asymmetry. If neutrinos are their own antiparticles, a hypothesis still under investigation, then their behavior in the early universe could have generated the necessary imbalance to tip the scales toward matter. Thus, the search continues, both in particle accelerators and in cosmological observations, to uncover the deeper principles behind this imbalance. Several theoretical frameworks have been proposed to explain why the universe contains more matter than antimatter. One of the most promising is baryogenesis, which refers to the general class of theories that explain how baryon asymmetry arose in the early universe. This mechanism typically occurs during high-energy conditions just after the Big Bang, where quantum fluctuations in symmetry, breaking processes could favor matter. Baryogenesis requires all 3 of Sakharov's conditions and often involves interactions outside the standard model of particle physics. One such extension is grand unified theories, GUIs, which attempt to unify the electromagnetic weak and strong nuclear forces under a single force at high energies. These models naturally allow for baryon number violating interactions and potentially strong CP violations. Unfortunately, many predictions of GUIs remain untested because the energies required to observe such phenomena are far beyond our current technology. Another theoretical possibility is electroweak baryogenesis, which involves the Higgs field and the electroweak phase transition in the early universe. If this phase transition was strongly first order, meaning it occurred rapidly and out of thermal equilibrium, it could provide the necessary conditions for asymmetry. However, the nature of this phase transition is still uncertain. Leptogenesis, as briefly mentioned earlier, offers another attractive explanation. This theory suggests that in the early universe, heavy right-handed neutrinos decayed asymmetrically into leptons and anti-leptons. These lepton asymmetries could then be converted into baryon asymmetries through processes involving sphalerons, hypothetical particles that mediate baryon and lepton number violation. This idea is particularly appealing because it links the matter-antimatter mystery to the mystery of neutrino masses, another area where the standard model falls short. Some even speculate that antimatter might exist elsewhere in the universe, perhaps in isolated galaxies or clusters. However, astronomical observations have not found any evidence for such regions. If they existed, we would expect massive gamma-ray signatures at the boundaries where matter and antimatter interact. The absence of such evidence suggests that the asymmetry is universal, not just local. Finally, There are multiverse theories which propose that our universe is just one of many, and perhaps in some of these others, antimatter dominated instead. While this idea is speculative and currently untestable, it highlights the philosophical depth of the question. The preference for matter in our universe may not be a universal law but a cosmic accident, one that simply happened in our bubble of the multiverse. While these ideas remain theoretical, they continue to guide experiments and shape our understanding of the early universe. The matter-antimatter asymmetry is not just a puzzle for physicists, it touches on the very reason for our existence. If the universe had been perfectly symmetrical, with equal amounts of matter and antimatter, everything would have annihilated into pure energy. No galaxies, no stars, no life. In that sense, the fact that a tiny imbalance occurred is nothing short of miraculous. This raises profound philosophical questions. Was this asymmetry an accident, a necessity, or something more? Was it the result of deeper physical laws we have yet to discover, or was it a one-time cosmic fluke that made our existence possible? From a scientific perspective, solving this mystery could lead to a revolution in physics. Discovering the mechanism behind the imbalance would almost certainly point to new physics beyond the standard model, potentially unlocking answers about dark matter, dark energy, and the unification of forces. It could also reveal insights into the structure of space-time, quantum gravity, and the early conditions of the cosmos. In this way, the question of why the universe chose matter is not isolated. It connects to virtually every other fundamental question in physics. There are also practical challenges and frontiers. Ongoing experiments at facilities like CERN, Fermilab, and neutrino observatories aim to probe deeper into CP violation, neutrino properties, and high-energy interactions. Future missions may provide more data about the cosmic microwave background, gravitational waves, and particle interactions in the early universe. In parallel, theoretical physicists continue to develop models that can be tested and refined. Each new piece of data brings us closer to understanding the origins of the cosmic imbalance. Yet, despite all these efforts, the answer remains elusive. Nature seems to have made a subtle but crucial decision at the dawn of time, and we're still trying to understand why. Perhaps one day we will uncover a deeper symmetry that explains the apparent asymmetry, or perhaps we'll find that some questions may forever remain just beyond our reach. Regardless, the pursuit of this knowledge is a powerful reminder of human curiosity and our drive to understand the universe at its most fundamental level. In the end, the mystery of why the universe chose matter over antimatter is both a scientific puzzle and a poetic reflection on existence. It challenges us to imagine what might have been and to appreciate the incredible chain of events that made our universe not just a sea of light, but a place where stars shine, planets form, and life thinks about the cosmos that birthed it.